All right, we'll get started. More people will probably filter in. So the first thing, just as a reminder, assignment 2 is due in 2 weeks. So I'll just go through it. So it's the same policy about slip days. If you didn't slip on assignment 1, you might as well slip on assignment 2. And if you slipped on assignment 1, then you'll have to hand it in by the deadline. That says 6 p.m. It should say 8 p.m. Let me fix that before. Okay, so you'll do a cognitive walkthrough. You'll choose one of these two tools. I suggest using the first one, but I always have the second one just as a backup option. It is free open source software. This is like kind of like a commercial product, but use the free version of the commercial product. So to do the cognitive walkthrough in step 1, you'll find 7 core tasks. So you will describe each task with 3 sentences and why it's like considered a core task as opposed to just like a task that's maybe not as important. Then choose 3 of the 7 core tasks that you propose, and you'll actually do the walkthrough for those 3. So try and choose 3 where you're going to have enough material to talk about, not like 3 things that are over like very trivially. I suggest using the same guidelines that we used for TOR. If you want to change them, that's fine, but you don't need to change them. They're very general and they work for all sorts of security software. So for each of the 3 you choose, just give a sentence for like why I chose this of the 7 that I could have chosen. This is why I chose this one, and then do the actual evaluation. So walk through the software and talk about how it does or doesn't match the guidelines at each step. I'd like 1 page per core task, no more. But if you have a lot of screenshots and things like that, you can kind of have like an extra page for screenshots, sort of in sum across them. So something like a 4-page kind of report. Again, the limits are mainly just so that the TA doesn't have to read lots and lots of material. Okay, so questions about the assignment? Okay. All right, so today we'll wrap up the attack tree on HTTPS. So last lecture, I'll just back up a bit. I'll go through these quickly. So we talked about how a certificate authority figures out that you actually own the domain that you want a certificate for. So there's 3 ways. It could email you like a code at admin@yourdomain.com typically, but it could be at other email addresses. You could put a file up, or you could put something in your DNS record that has your public key or your request for a certificate. So we went through the different vulnerabilities for email. Then we said the other 2 are like very similar. And then what I wanted to pick up on and just spend a few more words before we move on is we asked ourselves, one of the overlying issues with the certificate issuance is if the CA can figure out that Alice owns domain.ca, then it uses some method, right? So why can't the user just use the same method? Then we don't need a CA to figure it out, okay? So in theory, you could send an email every time, like say I go to concordia.ca, I've never been there before, I want to get their certificate. I could send an email to admin@concordia.ca and say, tell me your certificate. Or this is a certificate I'm receiving, is it right or wrong? And they could respond yes or no. And then that would effectively be the exact same security model as what's going on. But that's impractical. I'm not going to send an email to every domain that I visit. Even when I go to one website, I might pull in like 40 domains or something like that. So it makes more sense for one person to do it once than for all users to do it all the time. Okay. Similarly with retrieving it from the website. The other thing too is you only have to secure that process once. So the CA has to do it once securely, then everyone else is secure. Whereas users would have to do it securely every time. Now, the one method of all of them, though, that kind of makes sense is what if they put it in their DNS record? Because if they have their certificate or their public key or there's something, a hash of their certificate or something like that, sitting in their DNS record, I have to get their DNS record anyways. It's the same thing that the CA is doing to figure out who they are. So why don't I just get their information out of DNS? So this is a proposal. So people have proposed that, hey, why don't we just, everyone puts their public keys in DNS and then we're done. The problem with it, well, there's a bunch of problems with it, but the main problem is that we have no encryption. In particular, it's not so much about privacy, but message integrity between the user and their DNS. So in that case, if there's a man in the middle, they can change the response that you get back from DNS. And usually your DNS server is given to you by your Wi-Fi router anyways, or your ISP. And so, you know, the ability for them to attack you specifically would be very, very easy. Now, if DNS records were signed, then we could do that. Okay, then we could actually just put keys in DNS. And so there's a proposal to have DNS records signed called DNSSEC. It's kind of like rolled out, but not like 100%. And the proposal to put public keys in, given that you have DNSSEC, is called DATE. So this could potentially eliminate CAs in the future, but right now we don't really have wide adoption of DNSSEC, and therefore we don't have wide adoption of DATE. Okay, so there's two lessons that we can learn from this whole area of how do I bind a identity to a cryptographic key, which is the problem that we call PKI, public key infrastructure. The first is that certificate authorities, even though they have the word authority in their name, they're not actually authoritative over whose public key belongs to who. They don't know anything more than you do. So what's Concordia's public key? The certificate authority, it's not like they have an inside, like they know people at Concordia or something like that. They don't know anything more than you or I know, okay? They have a process and they've implemented that process and they've run it successfully for many years, okay? But at the end of the day, they're just relying on DNS working right, email working right, fetching things over HTTP working right in order to figure out whose key belongs to who, okay? So they're not really truly authoritative. And then the second lesson is that HTTPS is a cryptographic protocol. We're using keys and hash functions and signatures and encryption, as opposed to the normal web model where we use passwords and then maybe a cookie, a session cookie, or that type of stuff. But if you want to attack HTTPS, one place you could attack it is you could attack this issuance process. And there's lots of opportunities that if you know just the right password, for example, the password to an email account like admin@domain.com, to the DNS registrar, then you could attack this whole system. Okay, so it does kind of collapse back onto password-based security, even though it's usually a lot of fancy cryptography. Okay, so if we want to fill in our attack tree, this isn't the whole tree, but it's the subtree of obtaining a valid certificate. The subtree is, can we get the tunnel pointed at us? If we can get the tunnel pointed at us, then we can intercept HTTPS traffic. And one way of doing that is to get a valid certificate, okay? So we could try to hack into a CA, steal their key or subvert their process. So DigiNotar and Komodo are examples of that. We could subvert this issuance process. So for EV certificates, it might be some sort of social engineering attack. For automated validation or domain validation, for example, for the email, we could guess the password for the email account. We could intercept the email when it's being sent. We could try and get the email redirected to us through DNS. We could try and just own a particular email that a CA would send this type of challenge to. Or we could, I guess, I'm not sure what DNS attack is here, if it's different or the same, but we can change the DNS record so basically the email comes to us. Okay, and then the other two are kind of similar to above. And then we could also, to get a valid certificate, if the attack is happening in a country where the government, say, wants a certificate, they could lean on a company that is a CA in that jurisdiction. And then there's another interesting thing called interception proxies. I didn't talk about them. But there is some software that actually man-in-the-middles your HTTPS. That's basically how it works. So like examples of it would be parental control software or some types of like malware detection antivirus software. So the reason they man-in-the-middle HTTPS is because they want to see the content that's going across, and HTTPS prevents them from seeing the content. So what they'll do generally is they'll make a custom root certificate, and when you install the software on your computer, then it installs that in your root store. So now the software has a custom certificate, and then they can intercept your traffic. Now, it turned out that some researchers went to another place that uses interception proxies is organizations. So like Concordia, for example, if they want to filter traffic better than they are now, and they want to look inside of HTTPS, then what they could do is they could make everybody install on their computer a custom root certificate that they could use to intercept the traffic. So that would be a solution. And so there are people who sell this technology. So they sell the software for employers to install on employees' computers, and they sell the middle box, the server, that basically will do the man-in-the-middle attack. Because once you see an outbound HTTPS connection, you do have to decrypt it. You have to drop your key in, your fake key in, have the tunnel formed, but then you also have to form an outbound tunnel to the server itself. So it's not an attack. It's like a fairly sophisticated attack or feature or whatever you want to call it, because you do have to maintain an active man-in-the-middle connection. So there's companies that will sell you a server basically that will do this automatically. And a security researcher went to one of these big security conferences and was walking around talking to some of the vendors. And some vendors were promising something that seemed impossible. They were saying, we have this middle box. It will intercept all HTTPS traffic. And what makes us better than our competitors is you don't actually have to go around and install root certificates on your client's machines. Okay, it will just work. You plug it in and it will work. And the security researcher said that's impossible. There's no way that could work because HTTPS doesn't allow that. And so they obtained one of the boxes to try and figure out what was going on. And what they realized is that the company had actually got a root certificate. Sorry, not a root certificate, but they've got a certificate for issuing certificates. It would be like an intermediate certificate. But they had gotten a certificate that made them a CA. And they put this CA like certificate on this box, and they were selling this box. Okay? And so that's in violation of like what it means to be a CA. And the other problem with it is if someone could hack into the box, they could take the private key, because this is generating certificates on the fly, so it has to sign things. So the key has to be on that box somewhere. If I can extract that key off the box, now I have a certificate. I have the ability to issue certificates for any website that I want to. Okay? So it's a very dangerous it's a dangerous thing to have sitting on some product that you're selling. And so anyway, there was an investigation into it, and then these companies got their certificates revoked, essentially. And the CAs that had issued them the certificates also had their certificates revoked, or there was some sort of punishment against them. I forget the exact details. Okay, let's move on to validation. So like when you see a certificate, what are you actually looking for? What do you actually need to validate? Okay, so the first step is Alice will say, I want to talk HTTPS. The server will say, I talk HTTPS, that's fine. Here's my certificate. And then it will start negotiating the details. But when you get that certificate, you have to go looking through it, and you want to check and make sure certain things are correct. Okay. Now, they're kind of obvious things, but I just want to list them because there's actually been problems with all of them, even though they're pretty obvious things. Okay, so the first thing that we want to do is we want to see, is this certificate actually signed by a CA? And can we trace that CA back to, it's either signed by a root CA or it's signed by a certificate and I have a chain that goes back to a root CA. Okay, So if it doesn't trace back to a root CA, then I'm not going to accept that certificate. The certificate will have the domain name of, like it's for concordia.ca. And so you do a simple comparison, which is I'm trying to visit concordia.ca. I'm getting a certificate for concordia.ca. Are they the same website? Is the website I'm visiting and the website I'm getting a certificate for the same, right? So like you couldn't, if I was going to concordia.ca and Concordia sent me back a Facebook certificate, I'm not going to accept that as a certificate. The CA certificates, so CA certificates are just certificates. This is maybe best illustrated by just looking at it. So this is a little small, but this is like what Concordia's certificate looks like. Okay, so there's a bit more detail here than I alluded to, which is just like, it's just Concordia and the public key. There's more stuff here. We're not going to go through what all the fields mean. But anyways, this is what a certificate looks like for Concordia. If we go up the chain to Amazon, which issued it, this is what a certificate looks like for Amazon. And then Amazon has a root certificate, and this is what a root certificate looks like. And the point here is that Amazon can issue certificates. They can use this certificate to issue a certificate for any website on the internet, okay? But Concordia can't use their certificate to issue certificates, okay? Their certificate's like an end certificate, meaning all it does is it links their key and their identity together. It doesn't make them a CA, okay? But when you look at a CA certificate versus a website certificate, they kind of look the same. They have like all the same stuff, right? So like what makes this certificate able to issue new certificates below it, and what stops this certificate from issuing certificates below it, okay? And so the answer is there's a field right here called basic constraints, and it says certificate authority no. So this certificate is not a certificate authority because that flag is set to no, whereas if I go into the Amazon certificate and find the same field, basic constraints, certificate authority is set to yes, okay? So another check that you have to do, you have to check that the CA certificates are actually CA certificates, okay? So this is just showing the zooming in on that one extension. Certificates also have expiration dates. So you want to check what time is it, and when's the certificate valid for? And if it's past the expiration date, that you won't accept it. Now, sometimes this causes problems. It's not so common now because computers have gotten better, but in previous years, you would, okay, so let's say that you have a laptop. A laptop's a good example. The battery on your laptop completely dies. Okay, so your laptop is dead, all right? Now, when you turn your laptop on again, say a couple hours later after you charge it, does it remember what time it is? Generally it does, right? Okay, why is that? You might say, well, maybe it goes out to the internet and fetches the time and then reprograms it. Or somehow it's remembering the time even though it lost all its power, right? And so the answer is the second. It's remembering it because there's another battery, not the battery that you charge, but there's like a more permanent battery that remembers the time. But the other thing is true too. It also tries to fetch the time online. But if you don't have an internet connection, it won't do that. What would happen is people's, like that smaller battery that was in their computer after 5 years or something like that, it might die as well, okay? It's no problem for your computer, except for every time your computer loses power, it forgets what time it is. So then you boot your computer up, it has a completely wrong time, right? And then you start visiting the web because you don't notice that the time's wrong. And every website you go to, it's like the certificate's expired, it's expired, it's expired, right? And so the reason that's happening is because the local time is wrong, and so it's not matching the certificate validity period. But anyways. And then there's going to be a concept of revocation that we'll spend the last part of the lecture talking about. So I'll introduce that when we get there. Okay, so these are some of the checks. They're not all of them, but they're some of the key ones. And I pulled these checks out to highlight because historically there's been problems with all of them. So I'll just tell you some stories about things that went wrong. Okay, so the first story I'll tell you is about a bug. It's called go-to-fail, that's what people call it. So this bug affected Apple and their implementation of HTTPS, which is called Secure Transport. So it's their library that's used in Apple computers. And this was like a while ago in 2014. And just to fast forward, this is an implementation error. So there's no problem with HTTPS itself. It's not a problem with the protocol. It's purely the implementation of the protocol. So the problem was in software. And I'll try and sort of explain how the software worked at a very high level, pseudocode kind of level. So there were a bunch of conditions that were related to the certificate itself. So it was checking like basically these kinds of things. You know, is it actually signed? Are the certificates matching the domains? Are they actually CAs and things like that? Okay, so I had a whole list of conditions to check. All right, and the way they programmed it was they had a variable called check, a Boolean, or an integer if you want, and if the check passed, they would set it to 0. And if one of the checks failed, they would set it to 1. Okay? The default value was 0. All right? So what it would do is it would say, here's condition 1. It either passes or it fails. If it passes, we write a 0 into check. If it fails, we write a 1. Then we check whether the check is equal to 1. Okay? If it's equal to 1, that means it just failed. And if it just failed, then we'll go to fail. And go to fail means you just skip over the rest of the checks and go right to the end. And then the fail condition is to just return the variable in check. Because it failed, it will have a 1 sitting in it. Okay? The reason why we go to fail is if we're going to fail anyways, like say I check to see if it's signed and it's not signed, I'm not going to accept it anyways. So I don't need to bother checking everything else about it. Like, is it expired? Is it revoked? It doesn't matter. I'm going to reject it anyways at the end of the day. Okay? So that was why the logic of the routine was programmed this way. Okay? Now, it turns out that this code that is on the screen is fine. There's no problem with it. Okay? Go-tos are a little weird. Security people don't always like using them. But aside from that, there's no actual vulnerability in the code. Okay, so the vulnerability was introduced by a simple change of one line of code, which looked like this. So by accident, probably, but maybe deliberately, no one knows for sure, there was an extra go-to fail in one of these conditions. Okay, look like a copy-paste error or something like that. All right, now let's think about the consequence. Does this matter that we have this extra go-to fail or not? Okay. So what will happen is we'll go through condition 1, and let's say it passes. Okay, so then we write 0 into check. Check's not equal to 1. So we skip the next line, go to fail. Then we check condition 2, and let's assume that condition 2 passes as well. So condition 2 passes, so we put a 0 into check. Does check equal 1? No? Okay. So what's the next line of code that I'll execute? Say it loud. Which go-to fail? Why? Okay. So ifs are, this if is not true. So I'm going to skip, it says if this. So I'm going to skip over what it wants me to do if those conditions were true. Okay? Now go-to fail here, the second one's indented though, right? So is it part of the same condition or is it not? Okay. So it depends on the programming language. So some programming languages have conventions where tabs mean something. I forget what this was programmed in, like C, maybe Objective-C or something because it's Apple. But there was no like indentations mean nothing. Okay? All right. So if an if statement doesn't have braces around it at the end, then the automatic assumption is the next line is the one that you skip, and then you go on to the next line itself. Okay? So if there were brackets here, then both go-to fails would be inside the bracket, and then you would skip over both of them, and there's no problem with the code. Okay? But because there's no brackets, then when I skip the first go-to fail, but then I go to the second one. Okay? Now what happens? So I hit this second go-to fail. Where do I go next? Okay, so I hit the second go-to fail, but where do I go from here? What's the next line of code I execute after this? Okay, so I skip over condition 3 and 4. I go to return check. What am I returning in check?
The value in the check, that is 1.
Which is 1, which means it passed. Sorry, it would be 0 because it passed, right? Because if check was equal to 1, I would execute this. So I return 1. So the last thing I did was I checked condition 2. It passed. So I put a 0 into check. Then I go to fail, and then I return 0, which is a pass. Okay? So if I pass condition 1 and 2, the variable contains the fact that I passed, and then I just skip over 3 and 4, and then I return that it passed. Okay? All right. So do I ever check conditions 3 or 4 in this code? No. Okay. So if there's a problem with condition 1 or 2, I fail early and I return the fact that I failed. If there's no problem in conditions 1 and 2, I never check 3 or 4, even whether they're right or wrong. Okay? But what if 3 and 4 are important things? So I don't check them, so it doesn't matter. Okay? So it turns out that 3 and 4 were important things. So like one of the things that was checked was, does the certificate name, like the name that's the certificate's issued to, match the domain that you're visiting? Okay. So this, oh, by the way, this is like unreachable code. So it's just, there's no execution path that would reach it. Okay. So what that meant is, say I have a certificate for pulpspy.com. Okay. I see you going to google.com. You say, I want to talk HTTPS, I'm in the middle. And I say, yeah, I talk HTTPS, here's my certificate for google.com, and I give you my certificate for pulpspy.com, which has nothing to do with google.com. When Apple would process that certificate, it would skip over that check. Okay? So then it would say, yes, that looks great. It's signed by a CA, it's valid, it's not expired, it looks like a great certificate. I'm going to use the public key that's inside this certificate and assume that that's Google's public key. And then all of a sudden I'm in the middle and they're encrypting things for me, not encrypting things for Google. All right. So anyway, so this was a software vulnerability. How can we prevent this? So obviously we can always code things better and not make mistakes, but that's not always possible. Another thing that happened after it came out is there's a lot of vendors that create static analysis tools. And they said, oh, we took their code, because it was open. Apple's operating system isn't entirely open source, but some of their libraries are. And so this library is open source. And so they're like, we took Apple's code, we ran it through our static analysis tool, and it flagged this error, right? So that's good. It's true. It probably did flag that error. I don't dispute that. The problem with static analysis tools, especially at the time, is that in addition to that error, it was flagging 10,000 other things that weren't errors. So you still need a human to go through and say, oh, that one is actually an error, as opposed to all the ones that aren't errors. Okay. So the stories didn't really talk about how many false positives it also generated. So the best way to prevent this would be unit testing, where you have a bunch of bad certificates, and you're and you would have a certificate that's for the wrong domain, and every time you implement or do a software update on the library itself, you would run through your good certificates and make sure it's accepting all your good certificates, and you run through a bunch of bad certificates. Okay. And in that case, if you notice that it was accepting bad certificates, then you could figure out why it's doing that. Okay. And so then researchers said, that's a really good idea. Why don't we make every kind of bad certificate that we can think of and just run it through these libraries and see if there's other vulnerabilities that no one has caught yet. Okay. And so they do a process called fuzzing, where you do like Like, it wasn't just like they thought about like bad combinations. It's like they generated random strings or things that weren't in like Unicode and things like that. It was just a randomized algorithm that would basically throw like crazy sort of, they called them Frankencerts, like you take two certificates and you kind of like concatenate them together and things like that. They just made a whole bunch of crazy certificates. They ran it against a bunch of libraries, and they indeed found lots and lots of vulnerabilities that were then fixed as a result. Okay, what if I get a certificate, say for pulpspy.com, and I say I'm now a CA, so I create a fake Google certificate, and someone has to sign that fake Google certificate, so I just sign it with my private key that I have for my certificate, okay? And then I see a user that's going to Google, and I present the whole chain. I say, here's Google's certificate. It's signed by pulpspy.com, and pulpspy.com signed by whoever, and then it does indeed trace back to a root certificate. Okay, so what stops me from doing that? Well, I don't have that flag set in my certificate that says I'm a certificate authority. So I'm allowed to present my public key, but I'm not allowed to issue certificates against my public key. Okay, so we want to be able to check and make sure that this flag is actually set. All right. Now, there was a problem with this. It actually goes right back to the very early days of Windows, when Windows introduced Internet Explorer. It turned out that they were not checking this constraint. So for whatever reason, the developers had skipped over this. And it took a while for people to realize it, because most people are just use HTTPS as it was intended. So people weren't trying to do weird things like issue certificates with site certificates. But a researcher noticed it, and they issued it. They used their site certificate just like it was a CA certificate, and noticed that Windows wasn't rejecting those certificates. And so that was written up in 2002. So I misspoke. Internet Explorer came out in like 96 or 94. So this would have been like a later version of Internet Explorer. But at some point in time, they stopped checking this condition. Now, everyone said that's really stupid, right? Like, bad on Microsoft, they're dumb. Like, why did they do that? I don't know. We'll never do it again. It was embarrassing, but we'll never do it again, okay? Then the Apple iPhone came out, and Apple's like, we need a whole new operating system. We're not going to take the operating system that's on Macs. We need like a stripped down operating system because it's a mobile device. So we're going to rewrite the operating system from scratch. We're going to rewrite the internet libraries. We're going to rewrite the SSL libraries. Everything is getting rewritten. And guess what they forgot to do? They also forgot to check basic constraints. And then everyone said, okay, Apple, that's really dumb, bad on you. It's not going to happen again. Then a bunch of IoT devices came out. And again, they were like, okay, this is a super constrained device. We want to implement the minimal operating system possible. We do want to support HTTPS because we want secure communication, but we're going to like custom make a new library that's like a lot lighter than OpenSSL or something else that we could put on one of these devices. And guess what? They also skipped that things again, okay? But the good news is it's not going to happen again, okay? We did it 3 times. We've learned our lesson now, and so we're good. We're set for the future. Okay, another thing that could happen is what if you didn't get your certificate signed by a trusted CA? Okay, so you're supposed to get one that's trusted and it traces back to the root. What if you just said, who cares? Let's just make up a CA that doesn't exist, and it's not in anyone's root store, and we'll just send the certificate anyways. What's the worst that could happen? So the worst that could happen is that the user would get an error message. So back in 2011, they would get an error message that looked like this. Okay? So it basically says there's a problem with the website security certificate, blah, 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 blah. You can click here to close this web page, or you could just continue to this web page by clicking here. All right? Now, pretend you're a user. You want to check Facebook. And so you go to Facebook. It's not working. You're looking at this error screen. What are you going to do? If you're a novice user, you don't know what you don't know what a security certificate is. You don't know anything about computers. You can barely get online. right? You're probably just going to click continue to the website. If you do that, what will happen? The website will load, and from then on, it's like nothing happened. Okay? So there were attacks, people noticed, where that seemed to be like what the intention was. People were just making up certificates. They were completely invalid. They had no trace to root certificates, and they were just hoping that users would click through. And even if not 100% of users did, so this was sort of a nation state doing surveillance. As long as I get 70% or 80% of people that click through, then that's fine. I can at least look at what they're all doing on Facebook. Okay, and someone did a user study as well where they brought people into the labs, and they talked about like whether they would click through or not. And so like lots of people, like about half of people were saying that they would click through. Okay, now what the browsers did is they said, this is kind of on us because we're making it really too easy for users to click through, right? Even though it says it's not recommended, that's not really strong enough to like really prevent users from clicking through. And we're also using a lot of jargon, and we're trying to explain what's going on, and we're using terms like trust and certificate authorities and security certificates and stuff like that, right? So what we need to do is we need to still let users click through if they really want to, but we got to stop the sort of casual click-through rates, and we have to explain what the risks are better. So what Chrome did, Chrome sort of went first and led the way. So they changed their prompt. So it now says your connection is not private. Attackers may be stealing your information from whatever the domain is. For example, passwords, messages, or credit cards. And then there's a back to safety button, and there's no continue on button. Okay? So first off, the jargon is gone. So this is a much clearer message. It's easier to understand. Secondly, you can't just casually click through. Now, there is an advanced button, and if you press it, then there's a new prompt that comes up. Okay? And so advanced is more for the tech users. Now it switches to like more of a technical description of what's going on. There's the actual error code that's getting thrown, and there is the option still to proceed, even though if you want to. Okay, so now you have to read a message that's a lot clearer to understand. It makes it sound more dangerous. You'd have to click on advance, and then you would have to click on it to actually go through to the website. Okay, so it was a way of, you didn't take users' freedom away from them. Sometimes people just use, I don't know, self-signed certificates. It used to be a thing. Now you can get certificates for free, so it's less of a thing. But you know, sometimes people wanted to just use self-signed certificates and have their users accept them or whatever. So it was important that users do have the option of overriding it if they want. But anyways, so Chrome did it. They ran a bunch of user studies. They showed that the click-through rates went down to basically like small marginal levels. And then all the other operating systems sort of copied it. And so they all have very similar looking things today. To see what Chrome, or what Safari looks like today, we can go to this badssl.com, and we can try and find, say, a self-signed certificate. So this is what Safari says. It says, this connection is not private. The website may be impersonating badssl.com to steal your personal or financial information. You should close this page. Close page. There's a show details. Then it has some more text about it. And then to learn more, you can view the certificate. If you understand the risks involved, you can visit the website. Okay, so I could, and then if I click on it, there's yet another prompt that says, are you sure you want to go to this website even though it's not private? And if I'm like, yes, I really, really want to go, then I can get through it. Okay, but it's a lot harder to just kind of swat that kind of error message away, saying that's annoying me, like just like close it and then move on. And then the wrong host is probably the same. Yeah, it's the same error message, but. Okay, Now, another thing is when I get a certificate, I need to compare the website I'm visiting with the name of this website that's in the certificate itself. Okay, so I have two strings: the string of the URL that I'm visiting, the string that's in the certificate. They have to be the same. The domains have to match. Otherwise, I reject it. Okay. Now, when you parse strings, it's something that should be super easy, right? You just read in a string. But it turns out there's a lot of like security vulnerabilities around how you do something as simple as parsing strings, especially when things are written in different languages. Okay, so consider this. Let's say I go to a certificate authority and I say, give me a certificate. The domain I want is google.com nullcharacter.concordia.ca. Okay, so this is a weird kind of URL to request. Okay, but the CA is just a machine. It's not a human, right? It's just a machine. So it's going to look at this. It's going to send an email to admin at the domain that I'm requesting, right? And it's going to try and issue me the certificate. Okay, so if you're the CA software and you're looking at this string, what domain are you going to send that email to? So say it louder. Okay, so what I could do is I could say, I don't know what this null character is, like it's not a valid character, so I'm just going to kind of skip over it. I'll read this string in. I want to send it to the domain anyway, so I'm going to send it to concordia.ca. That's the last part of the domain. It's the top, sorry, not the top level, but the domain itself, as opposed to the subdomain. I can just drop all the subdomain things. Okay, so that's one valid thing that you could do. Okay. Another thing you could do is you could look at it and just say, I'm going to reject that string completely because it has an invalid character. Try again without using an invalid character. Okay. So there's at least two responses to this. It could be I'm not going to accept this at all because I don't recognize one of the characters, or it could be I'm just going to skip over or drop that character that I don't recognize. Then I'll process the string as well as I could. There's a third option. Does anyone know what the third option could be? Anyone who's programmed in C? So lots of programming languages like Java, if you have a string, it's going to, when you save the string to memory, it's going to like wrap it. So it's going to say, oh, this is a string, by the way, and it might put the length of the string and things like that. Okay, C's not like that. In C, if you have a string and you want to write it to memory, it just says, where do you want me to start? And it goes to that address and starts writing the string in. Okay, there's no header or anything. So it doesn't look any different than an integer or a data, arbitrary data buffer or anything like that. Okay, it doesn't distinguish between any of that. All it does is it starts at the address that you supply, and then it keeps reading, or sorry, it keeps writing. Okay, and then when it's done. Now, let's say you go back and you want to read that string out of memory. You'll go to that memory location. You'll start reading, but when do you stop? How do you know when the string ends? Because there's no length. You don't have a length for the string. So how do you figure out where the string ends? So in C, the convention is you put a null character at the end of the string. So this is called a null terminated string is the jargon for it. Okay. So in C, you get a memory address, you start writing your string in, and when you're done, you put a null character. And if I read it, all I do is I load that memory address, and then I just read until I hit a null character, and then I stop. Okay? So if C, a program written in C was reading this string, they would interpret it as google.com, because they would read to google.com, they would hit null, and they'd say, okay, this string is over, let's move on. Okay? All right, so those are basically the three options. You could reject it. You could drop the null character, in which case it's google.com.concordia.ca. Is this a valid domain? google.com.concordia.ca?
Yes.
Okay, yes, no? So it is a valid domain. Okay, there's nothing wrong with it. It looks weird, but com can be a subdomain of Concordia. So it's really Google's a subdomain of com, which is a subdomain of concordia.ca. So this is a concordia.ca domain with two subdomains. Okay, or you can terminate it at the null character, in which case you get google.com. Okay, so problems are, first off, there's no right or wrong thing. Probably the first one is the safest. Everyone should do that. But as long as everyone in the world does the exact same thing, like say everyone in the world does 2, then there's not a problem. Or if everyone in the world does 3, there's not a problem. The problem happens when different software does different things, okay? So for example, let's say the CA looks at it and says, I'm written in Java, so I'm just going to drop that null character. And so it's going to send an email to admin.concordia.ca, right? Concordia, the person at Concordia is going to answer that email. They're going to get a certificate. The certificate will be for the full string. Okay, so they'll sign off on the full string. Then what will happen is a user is going to Google, the attacker, Concordia in this case is the attacker, they drop in that certificate. Now let's say that the user's browser is written in C. Then when it says, oh, I just got a certificate for google.com null.concordia.ca, it says, I got a certificate for google.com. Am I visiting google.com? Yeah, I am. So this is the right certificate. I got the right certificate for the right website, even though it's the CA issued it for Concordia, not for google.com. Okay? And you can think of it in the vice versa direction as well, where the CA stops here and the browser consumes the whole string, although it works a little less well in that case. But anyways. Okay, and so it turned out that there were examples of CA software and browser combinations that would exploit this error. Okay, the final thing I want to talk about is revocation. Okay, so revocation, basically what happens if someone breaks into your server and they steal your key? Okay, if they steal your key, then they can impersonate you, they can get a certificate, or they can just use your certificate because they now have the key for it. And so they can take that key, they can go somewhere else on the network. Anytime a user tries to connect to your website, they can intercept that because they have the key. All right? Now let's say that Concordia wakes up and they go through their server logs and they realize that, oh, there was a phishing attack or something like that, and someone got access to the servers, and now we've noticed that it's been circulating out there. Someone, or maybe they go out and they see somehow they figure out that people are using their private key. Okay? What can the server do? So what we want the server to be able to cancel that certificate effectively. So the fancy name that we use for canceling something is revocation. So I want to revoke that certificate itself. Okay, and notice it's not good enough if Concordia just goes out and gets a new one. They could just be like, okay, that certificate's compromised, I'm going to get a new one. That doesn't cancel the old certificate. So now Concordia is using a new certificate, but the old certificate is still valid and the attacker's out there using the old certificate. So even if a user goes to concordia.ca and Concordia sends the new certificate, what the attacker will do is they'll just drop in the old certificate, and as long as the old certificate is still valid, then the user won't know the difference. They'll accept the old certificate. The user has no idea that the certificate changed, right? All you do is you get a certificate, you look at it, you do all your checks, and if they pass, then you say it's a valid certificate. And this old certificate was a valid certificate, right? Okay. Now, eventually certificates will expire, so you could wait 2 years. Then the old certificate's not going to work anymore. But 2 years is too long to wait for most people. They want to get rid of certificates right away. So we need a way to actually actively cancel the certificate. And the challenging thing is, how's Alice going to learn about it? How does Alice know that a certificate was canceled? Okay, so HTTPS has a couple options. There's two that are mainly used. The first one is what you do is every time you get a certificate, you're going to ping someone and ask them, is this certificate still valid? They're going to tell you yes or no. Okay, if they tell you yes, then you use it. And if they tell you no, it's been revoked, then you don't use it. Okay, now, who's that person that you're going to ping and ask? Well, the certificate itself will tell you. So the certificate will have the URL of a server that you can go to ask about whether the certificate is valid or not. And typically, 99.99% of the time, that server is going to belong to the CA that issued the certificate. Okay, so if I got my certificate from Let's Encrypt, then Let's Encrypt has a server somewhere, and you can ping Let's Encrypt and ask about whether my certificate is valid or not. So the protocol is called OCSP, Online Certificate Status Protocol. And again, it's one of these things that's in a certificate itself. So if we go back to Concordia and look at our certificate, somewhere in one of these fields, there'll be a thing for OCSP. Let's find it. So it's right here. And then there's a URL. You can see the URL is .amazontrust.com. Amazon is the certificate authority that issued the certificate. Okay. So what my computer did before it loaded this website and showed me the lock is it pinged this URL, and it basically asks, is this certificate valid or not? It doesn't send the whole certificate, it just sends a hash of it basically and says, is it valid or not? Okay, now let's say that, I know the slides have a lot of references to Facebook and almost no one uses Facebook anymore. I should update them. But let's say that you're a new CA and you're really excited because now you're a CA. You can make a lot of money issuing certificates to people. People will pay you. It's not a lot of work. You just run a server that sends some emails and things like that. And you offer really, really low prices. We'll set aside the fact that you can get certificates for free. And all of a sudden, Google, Facebook, Twitter, TikTok, whatever, they all sign up for you because you're cheap. Okay, so you're really excited because you're now the certificate authority for all those websites. All right, what's going to happen when this protocol kicks in? So you're going to have to put up a server that basically says, is Google's current certificate still valid or not? Right? When is somebody going to ask your server about that certificate? Every time they connect to Google. Okay? Let's say there's 100,000 people that hit Google in the next 10 seconds. 100,000 people in the next 10 seconds are going to hit your server and ask, is this certificate still valid or not? Okay? Plus all of Facebook users, plus all of Twitter's users. Okay? Do you have to have a pretty robust server? Yeah, almost like as robust as Google itself. Not quite, because the messages are a lot shorter. You just have a one round trip. You don't have to serve up a whole website. But basically, as much bandwidth as getting directed at a major website, you have to be able to handle that yourself. It's now getting directed at you. Okay. Historically, do you think CAs had that kind of infrastructure? No, not at all. Okay. So CAs, they didn't really think it through. They put up the server because it was required of them. But they just, they would get overwhelmed as soon as they signed up a big website. All right. All right. So then what should happen? So let's say that I download a certificate. My browser goes to the CA server and says, is this valid or not? And I just don't hear anything back. Okay. Because it's overwhelmed. I'm not getting a response. Maybe I time out and try again. But I've tried now for 5 seconds. I can't get a response from it. What should I do as a browser? So I have two options. One is I can display an error message to the user, okay? But now the user is going to get error messages on every website they go to because these servers are always down, okay? Or the other thing I could do is I could say, you know what, I'm just going to try and ask. If I hear that it's revoked, I'll definitely warn the user. But if I don't hear anything back at all, I'm just going to assume that it's good, okay? I don't want to keep the user waiting, and especially when you load websites and they're loading ad libraries and a whole bunch of things from 20, 30 different domains. It just takes one of those domains not to get a response for, and then the whole website hangs, right? So what browsers did is they said, okay, we're going to fail open. So this is a concept that we talked about before, which is that we try, and if it fails, the failure in this case is we don't get a response. We assume the best as opposed to assuming the worst, okay? And so let's say you want to attack a system. Let's say that you steal a certificate. It does get revoked. You find a user that's going to the website. You have the certificate in hand. You're going to man in the middle of them. But, oh no, you see that they're going to the OCSP server and they're saying, is this certificate still valid or not? And then you see that it's actually responding back that no, this certificate has been revoked, right? So you're in the middle and you see this message coming in that says the certificate is revoked, right? And it's going through you to the user. What are you going to do? You're just going to drop it. Because if I drop it, right, then the user is just going to assume, well, I didn't hear back. Okay. So what the adversary will do is they'll drop any response from the server, from an OCSP server that says that the certificate's revoked. Now, another thing you could do is you could actually just flip the response as well. So if the server says, yes, it's revoked, you could flip that to no, it's not revoked as well, okay? But you don't even have to do that much. You could just drop it. Now, you might say, well, how come you can flip that message? Isn't there message integrity on that, right? Like, why can I flip that message? Is there message integrity on a message sent to this server? So look at this URL and think about whether a man in the middle could change the traffic that's sent from this server to a user. So what do we think? Yes or no? So the answer is in this URL. So if the user is interacting with the server sitting at this URL, and there's a man in the middle, could the man in the middle change the traffic to and from this server? So how do we get message integrity? Let's say we want the property that any messages that are sent, if they're tampered with in the middle, then we're going to at least be able to detect that they were tampered. What's the protocol that gives us that property? HTTPS. Okay, so HTTPS is the protocol that gives us message integrity. Is this going over HTTPS? It's just going over HTTP. How do I know that? Okay, because the address is HTTP here. Okay, so if you see HTTP, that means there's no message integrity, so anyone can change it. That's why like downloading JavaScript over HTTP and all that stuff is dangerous. Okay, anyone in the middle can change it. Why is this not over HTTPS? It seems pretty important, right? I'm asking whether a certificate's revoked or not. Presumably, I'm asking it because the only danger to me from a revoked certificate is if there's a man in the middle. If there's no man in the middle, it doesn't matter whether the certificate's revoked or not, really, right? So the danger with me, the only time that a revoked certificate really matters as a user is if there's someone in the middle that's trying to impersonate it, okay? So if they're already in the middle and my protocol is asking through the person in the middle whether something's valid or not, it's asking over a protocol that's not secure. And so even if the response back is no, it's been revoked, then the person in the middle can just flip it to yeah, it's still valid, right? Like what's even the point? There's no point in even doing it, right? So what I want to do is I want to flip this to HTTPS. If I flip it to HTTPS, my problem's solved, right? Then it could still drop the packet in the middle, but it couldn't change the response, the attacker itself, okay? Why can't this run over HTTPS? Okay, so let's walk through slow motion what would happen if I made this HTTPS, okay? So what I'll do is I'll go to, let's use Concordia as the example. So I go to https concordia.ca and I say, hi, I want to talk HTTPS. Do you talk HTTPS, yes or no? Concordia says, yes, here's my certificate, okay? So that's the first step. I go into the certificate and I say, okay, I got to check whether this is revoked or not. I find the URL, which is now HTTPS, and I say, okay, I'm going to ask this server whether it's revoked or not. Okay? What does that mean, I'm going to ask this server whether it's revoked or not? Well, I'm going to go over to ocsp.globalsign.com, and I'm going to say, first thing, do you speak HTTPS? Yes or no? And GlobalSign will say, yep, I speak HTTPS. Here's my certificate. Okay? So now I have GlobalSign certificate. Now I say, is this certificate revoked or not? All right. Is it revoked or not? Well, I go into the certificate, I find the URL for its OCSP responder. And then if it's over HTTPS, I go to that responder and say, do you speak HTTPS, yes or no? It says, yes, here's my certificate. Now I have another certificate and I have to ask whether it's revoked. So I have to find the URL in it, and it's over HTTPS. So I go somewhere else, and it never stops, okay? I can never get out of that loop, because I can never check whether something's been revoked or not, because every time I check, I get a new certificate, okay? So that's why it has to strictly be HTTP. If it's HTTPS, you get in this circular dependency loop where you can't break out of it, okay? So the adversary has two responses. One is, because browsers are not strict, it could just drop the response. But if browsers tomorrow said it's important to enforce OCSP, then they could also just change the response in the middle. Now, browsers have gotten strict recently. Okay? They started getting strict for EV certificates. So they said for EV certificates, you have to have a responsive OCSP server. We're going to test it periodically. I'm not sure how exactly they assure it, but it's like one of the assurances that they have a certain amount of uptime. Okay? So there was actually an intermediate period where a bunch of browsers just completely turned off OCSP. They said it doesn't do anything anyways, let's just turn it off. And then, so there's a period where they just dropped it, then they turned it off, and then now there's the period where it's turned back on again, and it for some kinds of websites, for some types of certificates, and it's very strict, so they have to respond. Okay? But the second attack still works. You can still just change the response because it's still just over HTTP. Okay, so is it valid? No. You just flip it to a yes. Okay, the second option that we can do is we can use certificate revocation lists. So these are lists that are sent, or they're posted by the certificate authority. So it's almost the same idea. The difference is with OCSP, when I get a certificate, I go and ask whether the certificate's revoked, yes or no. So it's like an online protocol. That's why it's O online. It's like I ping it at the time I'm looking at the certificate. With CRLs, every day I go to the CA, I say, give me your latest list. And it has a list of a whole bunch of certificates of websites I'll never visit, right? But then it may have some on there that I do visit. And so then when I get a certificate, I check it against the list, which I downloaded. And then if it's on the list, I don't trust it. And if it's not on the list, then I let it go. Okay. So browsers will do this automatically for you. So Chrome has something called CRLS set, and it will go automatically around to CAs and it will get it. This is like very old data, so I don't know how accurate it is today, but at the time, CRL set was like very incomplete. So 75 or 85% of certificates were missing from CRL set back then. So you were only getting coverage of like 25% of the CAs itself. But anyway, this is a second option that can be used. A third option, I forgot about that there's a third option. This option actually probably makes the most sense. It's just unfortunate that it didn't work for like kind of implementation reasons. The problem with OCSP is that the big problem with it is that the server gets overwhelmed. Okay, the server gets overwhelmed because every visitor that goes to Google is also visiting the OCSP server for Google's certificate authority. So what about this as an alternative? What if Google themselves go to the OCSP server and say, tell me whether this certificate is revoked, yes or no, and sign it? Okay, so I get back a response, it's signed. Now when users come to me and ask for my certificate, I send them the certificate and I also send the signed OCSP response that says it's still valid. So I send both of those things to the user. Now the user doesn't have to go over to the server. So Google can do it once. Say maybe they're only valid for 3 hours. That's fine. Every 3 hours Google goes, but the server is only getting one request every 3 hours, right? and every user is getting the response from it, okay? Because Google has to send their certificate anyways, right? So they can just add the response on. So this is called OCSP stapling. So you basically just, you get it signed, you throw it in with your certificate, you give it to the user. Now the user doesn't have to go and check themselves. This worked for a lot of the internet, but there's certain like backbone internet computers that do like traffic shaping. And so what they do is they do like some sort of deep inspection of packets. Deep doesn't mean that they're necessarily reading the content, but they're at least reading the headers. And when you threw this extra information into the protocol, there wasn't a field for it that existed. And so these middle boxes would just be like, I don't know what that is. This looks malformed because there's this extra information in a field where there shouldn't be. I'm just going to drop it. Or maybe I crash because I see it, but I think it's more likely that they just dropped it. And so unfortunately, this didn't work because there were a bunch of middle boxes that were just dropping this information. Now, eventually in time, if middle boxes update, this could come back. So this is something that's just, it's sort of an implementation issue away from being deployed. And it's probably the most sensible of all three of the options. Okay, another option for an adversary is they could just not use a certificate at all. And what I mean is like not use an invalid certificate. I mean like just not use a certificate. How do you not use a certificate? Well, you only need to present a certificate when the user asks whether or not you speak HTTPS. Okay, they ask, do you speak HTTPS? Then you have to send a server, okay? But what you could do is, what the adversary could do is they could try to make it so that the user never asks. So basically they go to HTTPS and they never leave, they go to HTTP and they never leave HTTP for HTTPS, okay? So a common template for websites that's now thankfully mostly eradicated, but what would happen is you go to a website, say it was like concordia.ca, and there might be a sign-in thing right in the toolbar, like username, password. Maybe you have to click on something, but it might just take your username, password right from the root screen. And what the website would do is it would come over HTTP, okay? But there would be a field that would accept your password, and when you click the submit button would send it over HTTPS, okay? So the submit button was wired up to send it over HTTPS. You as a user looking at the website, you don't know whether that's the case or not. Okay, it's in the HTML of the website. So when the user clicks that submit, you take that information and you post it somewhere. What's that URL? That's in the HTML itself. But the websites were coded correctly. They weren't sending users passwords over HTTP. They were sending them over HTTPS. Okay. The problem though is that they were doing it from an HTTP page. Okay. So if I want to know, does this thing go over HTTP or HTTPS, I would have to like go into inspect element. I would have to find this like sign in button, and then I could see, okay, it's sending it to, HTTPS hub.concordia.ca. So because there's an S in the HTML of this website, that sign in button is fine. There's no problem with the sign in button itself. Okay. Okay. Now the problem is if this page comes down over HTTP, okay, so even though the link links you to HTTPS, if the page itself comes down over HTTP, can the adversary change that page? If it comes over HTTP, it can. Okay, you can always change anything that comes over HTTP. Okay, what can they change about the website? So yeah, they can change anything they want. Could they change this sign-in button if they wanted to? Yeah. Sure, why not? Could they change this URL if they wanted to? Yeah. Could they send it to HTTP instead of HTTPS? Yes. If they did that, then if a user typed in their password and clicked sign in, would it go over HTTPS or HTTP if they changed it? It would go over HTTP. Could the adversary read it then? They could, because they're in the middle. Okay? So there's a basic attack, which is if you see any website that's coming to you over HTTP, what you do is you quickly parse the source code of the website, And you don't even have to be that smart. You don't have to go in and figure out what's this button do and like all that type of stuff. You do a much simpler attack where you basically say, anytime you see HTTPS:// replace it with HTTP://. Done. Okay? And so what it will do is it will do that for every single HTML page that it comes. And what will end up happening is the user will never leave HTTP because every time it clicks on a link that would redirect them to HTTPS, it's now been rewritten as HTTP. Okay? So they'll just stay in HTTP forever. Eventually they're going to put in username, passwords, whatever, and then those things are going to go over HTTP. Okay? So there's a tool called SSL strip that automates this. This is an older tool. I don't know if it still works today, but anyways, and the whole thing is called SSL stripping, this particular attack. Now, your browser will warn you, though. If you do try and put your password through an insecure channel, the browser itself will also populate a warning that says you're about to submit information that's not over a secure channel. Do you want to proceed or not? And again, the user could click through that if they wanted to, so it's up to the user. Okay, so once you're on HTTP, the man-in-the-middle adversary can basically keep you there, so they can move the entire site. This should, say HTTP, not HTTPS. So they can move the entire site to HTTP. All right, here's another attack. All right, so here, tell me what you see when you look at this picture. Okay, how many browser windows are here? Okay, so we call this a pop-up. Do you see pop-ups a lot? Yeah, yes, no. Okay, not as much as you used to. I guarantee you, like 10 years ago, 20 years ago. Most times things pop up in new tabs. And if they pop up, they usually don't pop up with a full browser, Chrome or whatever. It's more like a message or something like that. But it used to be the case that every time you click on it, it was a different website than what you were on, they would just open a whole new window. So you would get these pop-up windows. And then sometimes you go to a malicious site and it would open like 100 pop-up windows. But anyways, okay, so this is what we call a pop-up window. Okay, the inner site, you can't really read it, but what do you think the smaller pop-up is for? So for PayPal, and if you looked at the URL, you would see that it indeed says paypal.com. It's an EV certificate, so it's green, and there is a lock, and it says PayPal Inc., so you know it's the company PayPal, it's not some other weird PayPal. And all of that stuff looks fine, okay? Now there's a login screen here. So let's say I put my email address in, I put my password in, I click login. Is that password sent securely or not? So I'm putting a password in the password field, I'm clicking logged in. I'm on a website. The website starts with HTTPS. There is a lock. So the initial website, say it louder. Okay, so it's true. So there is the other window is loaded over HTTP. If I have two windows open and one's over HTTP and the other one's over HTTPS, is my traffic going over HTTP or HTTPS? So if I'm in window 2, that stuff's going over HTTPS, and everything I'm doing in window 1 is going over HTTP. So that shouldn't be a problem. Now, I know you all know there's an attack here, so no one wants to say that this is fine. But is it fine? Okay, so if everything is the way I described it, it actually is fine. Okay, there is a lock. It is over HTTPS. You can submit a password over HTTPS, and that's the guarantee of the protocol, is it will go to paypal.com or whatever the certificate's for. They're the ones that have the decryption key, and they can decrypt it. Okay? The question, though, is there actually a lock here? Why is there a lock? Where is the lock? Maybe that's a better way of putting it. So the lock is right here, right? Is that an HTTPS lock?
I don't know. I can't see it.
Yeah, you can't really see it. Okay. let me ask you another question. Are you actually looking at two browser windows here? Is there any other thing that you could be looking at? Say it. Okay, so let's say it's an iframe. But what does that mean?
It's a window that is open through another window, so it's like a embedded baby.
Okay, if it's embedded, it's fine. It's actually no problem. So forget about that. But you're on the right track.
The traffic is going through the HTTP as HTTP, so they can see everything still.
But how? How's that possible? Okay, go back to the original question. Are you looking at two browser windows? Is there any explanation other than you're looking at two browser windows? So the second browser window, the smaller one, is completely contained within the website, the bigger website itself, right? Could this just be a picture that they're showing you on this outer website?
Yes.
It could be, right? Could it be a little more fancy than a picture, like an HTML where, like, if I click here, it would actually like give me text and things like that? But this whole thing, the close button, the expand button, that's not the operating system. It's not actually the browser. It's just something that's in the content of the website itself. It could be, right?
Yes.
Okay, so that's what a picture-in-picture attack is. So the picture-in-picture attack is you show what looks like a pop-up, but it's not actually a pop-up of the window. It's just in the content of the website. You can make it so that if the user clicks on it and drags it around, it actually drags it around. But what the user couldn't do is drag it outside of the content of the website itself. Okay, so when we look at a browser window, just for terminology's sake, you have the content of the website, which would be in this square for the outer website. And then all this extra stuff like the forward button, back button, URL, it's actually called the Chrome of the browser. So that's like where the Google Chrome gets the name from. But it's called the Chrome of the browser. So you couldn't drag the Chrome of the inner thing over top of the Chrome of the outer because it's actually part of the website itself. Okay? But if this is just inside the website, is this actually an HTTPS connection? It's not, right? It's just a picture of a lock and some text that says it's going over HTTPS. Okay, so if you put your username password in there and you click it, where it actually goes is it goes to the original website itself, which could also be over HTTPS. It's just as long as it's adversarially controlled, then they're going to get your username password. Okay, so because of attacks like this, we no longer really prefer pop-up windows. Okay, we really like to put things in new tabs. They're also annoying for a number of reasons as well, and so you don't get like the traditional pop-up. I don't even know if it's possible to create a true pop-up where it has the full browser Chrome for things. Like you can get pop-ups that don't have browser Chrome, but I think I don't think this is even possible to do anymore with modern browsers. Okay, so the adversary controls the outer website. They create a fake browser window. And then we also see this instead. Sometimes it's like alerts, like operating system alerts that may or may not be right in the website itself. So it might be part of the content of the website itself. The other thing about these alerts, by the way, is the website that issues it is free to set the text to whatever they want. Okay? So if they want to put in custom text, they can. The problem is all you can do is click OK as a user, maybe stay on page or leave page, and that doesn't help the adversary. Like, it doesn't matter what I click here or here, it's not going to help the adversary. Okay? So it's not really viewed as an attack because the adversary can create a fake error message, but at most the user is just going to click on it and it's going to go away. Okay? So what fraudsters will do is they'll try and put what they want you to do that's bad into the content of the message itself. So you can see these messages are like, you got to phone this phone number, right? So they make up some fake thing about like there's a problem with your computer, and you can't fix it from clicking on things on your computer, but you could fix it by like phoning something or something in the content or visiting this URL, that kind of thing. Okay, so if we complete our portion of the attack tree, we want to subvert server authentication, which is a fancy way of saying get the tunnel pointed at us. Okay. We might get it through an invalid certificate, and there was a whole tree that we had expanded a few slides ago. But other options would be I could just use an invalid certificate, I could use a revoked certificate, or I could just not use a certificate at all. Okay. If I want to use an invalid certificate, I could just make one up. The user will get an error, and I just hope that they click through it. If there's some sort of flaw in the implementation of the user's SSL, then I could also do it. And then there's some cryptographic attacks we didn't talk about, but you could try and exploit collisions between certificates. I won't go through those details. Okay. Now, let's say you're able to steal what was a valid certificate, but now it's no longer valid because it's been revoked. Then what you can do is you can attack the revocation check itself. Or the other thing you could do is just not use any certificate. So you could strip all references to HTTPS, keep the user only on HTTP. You could spoof the browser Chrome so it looks like they're on HTTPS, but it's really just part of the content of the website. And then there's other things too, like you can put locks on this website. Like you could say username, password, you could have a picture of a lock. Does that mean it's going over HTTPS? It doesn't, it's just a picture on the website. You could put a picture in what's called the favicon of a website. The favicon is like the little logo here. So there's a little lock beside bad SSL. Because there's this blue lock here, does that mean that this is a secure website over HTTPS? Not necessarily. It's just an icon that you can put. And browsers used to put those icons up here beside the URL. So it was actually confusing because you could get the lock like pretty close to where the lock would be. Now it just puts them in the tabs itself. But okay, so questions about any of these attacks? Okay. All right, so the full attack tree you can see here, or it's on Moodle if you want, or on the website. And so you can see all the different things that we talked about. All right. So what are the sort of takeaways from doing this big exercise of doing an attack tree? Okay. So first off, you got to see what an attack tree looks like with a thorough example. So many classes ago, we talked about breaking out of a parking garage without paying. That was kind of a toy example. This is what an attack tree would look like for a thorough example. And this is like pretty professional or like it's pretty comprehensive and complete. We needed to know a lot in order to do this. So even though it's a high level methodology, attack tree you can use with analyzing the security of anything, it still can allow you to go into a lot of detail. Now the level of detail that you put into this, it depends on you doing the attack tree. So you could do a very like lightweight attack tree for HTTPS as well. So basically the amount of depth is up to the person making the tree. And so you can put as much depth into it as you want. And you can actually communicate like pretty deep technical things using this as well. So you need some domain knowledge in order to do the tree. Another thing I like about this methodology is some of the attacks were like not technical attacks. It was like the government goes over to this company and says, give me a certificate. Or someone who used to work at Microsoft goes in and they still have their ID and so they show their ID instead, okay? Or I guess the password for your email, whatever, okay? So these types of attacks you can put in an attack tree alongside the cryptographic attack where you're, messing around with block ciphers and things like that, okay? Both of them can live together. So the attack tree is nice because you can include all kinds of attacks. You can have side channel attacks, you can have human-based attacks, social engineering, you can have very technical attacks. All of them can live together in the same methodology. Okay, so it gives you a lot of breadth. The next thing is the tree gives you two things. So one thing it does is it gives you structure. So if we just actually go back here, you can see there's a pattern here. Obtain a valid certificate, an invalid certificate, a revoked certificate, use no certificate. And once you sort of establish that pattern, it's easy to say, is there another thing that we could have done? Like what about an expired certificate? Use an expired certificate, right? So that's something we don't have in the tree. Maybe we need a node for that, okay? So once you see like sort of commonalities between it, it's easier to find other possible attacks. And then the second thing is it will tell a complete story like when you start at the root node and you go to one of these leaf nodes itself, okay? So my goal is to break, I know you can't read it, it's too small, but my goal is to break HTTPS. How am I going to do that? I want to read everything that's going over HTTPS. Well, the user has a tunnel and I can't read what's going over the tunnel, so I'm going to get the tunnel pointed at me. How am I getting the tunnel pointed at me? Well, I need a certificate because tunnels end at certificates, okay? So if I can get a certificate, then I can end the tunnel at me. So I'm going to do that. I'm going to get a certificate. But I can't just go ask for a Google certificate because I'm not Google. So how am I going to do that? Well, what I'll do is I'll go over to the certificate authority and I'll tell them that I'm Google even though I'm not Google, okay? Now that's going to be a problem because the certificate authority is going to say, well, you have to prove that you're Google. We're going to send an email to admin@google.com and it has a password in it. And you say, oh, that's great. What I'm going to do is I'm going to intercept that email. So when it goes from the CA, it's not encrypted. I'm going to intercept it. I'm going to get that password. And when I get that password, I'm at a leaf node here. Then you can backtrack and you can say, okay, I got that password. So now the CA believes I'm Google. Now they give me a certificate for Google. Now that I have Google certificate, I can get the tunnel pointed at me. And now that the tunnel's pointed at me, I can read all the traffic that the user's sending to Google. It's going through me now. And I can decrypt it because I have that certificate. Okay. So the attack, as you sort of go from leaf to node, it tells a story of what the attack is. And then you can backtrack back to see that it satisfies all the constraints that you need it to. Okay. And you can do that with any path through the tree. So they're nice, like, kind of things for, so sometimes for projects, like students will do this. You don't need to do an attack tree, by the way. I should emphasize this as many times as I can, but sometimes students think they have to do either an evaluation methodology, like an evaluation framework, or an attack tree, or a cognitive walkthrough. For the projects, you don't have to do anything we talked about in class. You can do something that's not covered in class in terms of the methodology, as long as you're talking about what the security is. And if you do an attack tree, I want just a project that is just an attack tree. I don't want an attack tree and an evaluation framework and a cognitive walkthrough. I'd rather have one really in-depth thing than a whole bunch of like things that aren't in-depth itself, okay? But anyway, so you could do an attack tree for a project, but also in industry, like say someone wants a report on the security of things or what the attacks are. Attack tree is a nice way to get everything on one piece of paper. You won't be able to understand the attack necessarily from the tree itself. Like you can see the words in the boxes, but there's a lot of technical detail that goes into it. So it usually would be accompanied by a write-up where you would be explaining all of the nodes itself. But it kind of situates the attack and you can kind of see it alongside the other kinds of attacks. And then from a defense perspective too, if you're really worried about, say, this attack here, you know, if you can defend at any of the nodes leading to the attack and cut the attack off there, then you can prevent the attack from happening as well, okay? And the higher you can sort of implement a defense, like if I can implement a defense here, then it cuts off this whole subtree, right? And so it also helps you plan out like where you might put defenses in as well, okay? So it's a pretty useful tool, even if it's like relatively simple. Okay, questions about the attack tree or HTTPS or anything that we've talked to up to this point? Okay, seeing none. All right, so that's it for these 3 lectures. Next class, we'll switch topics again. I forget where we're going next. I think we're going to same origin policy. Let me just double check. Okay, yeah, so the next 2 classes, we'll talk about policies, and then the last 2 classes, we'll talk about what's called social engineering as well. Okay, so that's it for today, and I'll see you all next week.